Hello everyone and welcome to this talk. All your Ether are belong to us, or how to hack Ethereum basic dApps. Who am I? My name is Gonzales. I've been having fun for around 11 years working for offensive security field. Ethical hacking, red teaming, and all the fun stuff. Currently, I'm working as a lead offensive security engineer at Halvor. It's a specialized company for cybersecurity in blockchain and crypto world. Also, I'm postgraduate instructor in ethical hacking courses. If you enjoy this talk, please reach out to me in LinkedIn and Telegram and say hello. I will appreciate it. Okay, what are we going to see today? We are do a recap about blockchain. We'll have a general introduction about smart contracts and the meat of this talk. What are the decentralized applications of dApps, how they work, and especially how to hack them. Let's begin. Blockchain 101. What is blockchain? As the name suggests, it's a chain of blocks that contain some information. Blockchain became popular for around 2009 with the appearance of Bitcoin. But be careful, Bitcoin is just one of the main applications that blockchain can have. Actually, blockchain is a distributed ledger, so it's completely open to anyone who wants to participate. And they have an interesting property. Once some data is recorded in the blockchain, it's extremely difficult to modify it. So how does it work? Let's take a closer look to a block. A block has data, has a hash of the block, and has a hash of a previous block. What kind of data has the block? Well, it depends on the blockchain. For example, if we are talking about a blockchain for Ethereum, we have detail about a transaction. So we have the sender, we have the receiver, and of course, we have the amount of coin involved in the transaction. Then we have the hash of the block. We can compare the hash with a fingerprint. So every block has a unique hash. And let's see, if we modify just one bit on the block, the hash now it's completely different. If we modify another bit of the block, the hash is completely different. So that's why hash is very useful to verify if someone has tampered our block. Finally, we have the hash of a previous block. With these three elements, we can create a chain of blocks or blockchain. The big question here is, what happens if an attacker wants to modify or tamper our block? Well, blockchain has two powerful mechanisms to avoid it. The first one is called consensus. Regarding Ethereum and Bitcoin, the consensus mechanism is called proof of work. How does it work? We have to solve a crypto challenge. What does it mean? If you want to create a block, you have to find a number that makes your block compliant with a specific numerical condition. And as far as we know, there is no mathematical formula to calculate the number. The only way is to guess the number. And because you have to guess it, the more computational resources you have, it's more likely that you will be able to create the block. The mean time for block creation in Bitcoin is around 10 minutes. In other blockchain, it varies. And this process is called mining. Obviously, the ones who participate in the process are called miners. The second mechanism is called peer-to-peer network. Let's remember that blockchain is a distributed ledger. So every participant in the network has its own local copy of the blockchain, right? So imagine a user wants to create a new block. He shares the block to everyone in the network. So every participant is going to verify if the block is compliant with the specific numerical condition I mentioned earlier. If so, they will add the new block to the blockchain, to their own local copy of the blockchain. That's how they get consensus. Awesome. Now, what happens if an attacker wants to create a fake block? So the participant will be able to verify that the new block is not compliant and the new block will be rejected. Perfect. Now, what are smart contracts? Well, smart contracts are very similar to traditional contracts. They both have terms and conditions. The big difference is that a smart contract is digital, so that's why the terms and conditions are expressed in code. When you compile that code, you can store it in the blockchain. So, due to the fact the smart contract is inside the blockchain, it's accessible for everyone. Everyone can read the code. Everyone can interact with the smart contract. Obviously, depending on your authorization level, you can do an stuff or another. But at the end of the day, you can interact with the smart contract. And there is consensus about the outcome. Let's see an example. For sure, everyone knows about crowdfunding platform. For example, Kickstarter, Indiegogo, etc. So we have a product team who wants to raise money, and we have supporters. If that product team gets or reach a monetary goal, the money goes to the product team. Otherwise, if you don't get the goal, the money is returned to the supporters. How does it work in the blockchain world? So instead of having a company like Kickstarter, we have a smart contract. So the supporters give money to the contract, and the contract verifies if the monetary goal is met. If so, they give the money to the product team. Otherwise, if the goal is not met, they return the money to the supporters. What is the logic inside the contract? Easy. We have a conditional expression. Very, very straightforward. The goal is met, then give money to the product team. Otherwise, return the money to the supporters. There are many use cases for many industries, for banking, insurance, delivery, music services, streaming, video games, exchange application, and a huge, etc. Very interesting. What are the blockchains that support smart contract nowadays? Well, we have many of them. The main one is Ethereum. And if you want to create smart contracts for Ethereum, you have to use Solidity programming language. It's not the only one, but it's the most popular. Okay, regarding Ethereum, we have external user and we have a smart contract. They both are identified with a 20-byte hexadecimal address. And what can we do inside the blockchain? For example, we can send money. The native coin inside Ethereum, it's called Ether. So you can send Ether to another user, for example. Or you can interact with the smart contract. And what does it mean? That you call a function from the smart contract. And the smart contract can interact with another user. You also can have chain reaction. A user call a function from a smart contract. The smart contract interacts with another smart contract, and this contract interacts with a user, a chain reaction. Great. Okay, we have a user that wants to call a function from a smart contract. I mean, he wants to transact. And for the user to transact, he has to sign the transaction. Why? It's a way to demonstrate you are the owner of the transaction. So you need a private key. Once you sign the transaction, you send to the network, the Ethereum blockchain. So participant can decrypt the transaction because there are public keys in the network, because they are public. In a day-to-day operation, the private you don't sign the transaction in a manual way. There is a tool, in this case, a crypto wallet, that you use to store and manage the different keys you can have. You can have many examples. We have MetaMask, Trezor, etc. For example, MetaMask that is here, it can be used like a plugin in the browser. Very easy. So, what are decentralized applications or DApps? Let's see. The best way to understand is to see a real example. So I introduce you to Synthetics. It's a DApp that allows you to interact with financial assets. So as you can see, it looks like a normal web page. We can go to the staking option, for example, and we can see in the upper corner that we are not connected. So we try to connect with a wallet, appear many options. I will try to connect with my MetaMask wallet, and then I select the first address here. As you can see, the address finishes in D1E6. Now you can see in the upper corner that I'm connected with the address that ends in D1E6. That's it. Now I'm connected with a DApp, and I can interact with a different menus in the dashboard here. Great. We can have many examples, financial application or DeFi. We have marketplace similar to Amazon, similar to eBay. We can have social network like YouTube, for example, similar to YouTube. We can have video games, we can have exchange application, and many other kinds of application. Great. What is the architecture inside a DApp? We can compare it with a web application. For example, in a web application, we have a browser that retrieves static files from a web server. With the static files, I mean HTML, CSS, JavaScript. And then the browser connects to a backend, for example, through API. The backend connects to a database, and so on. On the other hand, the decentralized application or DApp, we have that static files and backend is stored inside a blockchain. The most used architecture is a hybrid one, that static files are retrieved from a web server and the backend is inside the blockchain. The big question here is, how is it possible to store backend inside blockchain? What is the magic behind that? Let's see. In the left side, we have the browser and the web server, and in the right side, we have the Ethereum blockchain. For them to communicate, we need a bridge. A bridge can be any computer, any server, any cloud services. The key here is to turn this bridge, this computer, to a Ethereum node. How can we get that? We can install a tool like Get, we can use cloud services like Infura, etc. The thing is, once you have an Ethereum node, you have your own local copy of the blockchain first. Then you install with the smart contract. Then we install a component called Ethereum virtual machine that allows to interpret the commands to the smart contract. And we have interfaces. Interfaces are the doors that allows us to communicate with the external world and within internal process. So the browser retrieves static files from the web server. HTML, CSS, JavaScript. One of the many JavaScript files is a one that allows us to build a transaction. In this case, I'm using Web3.js, very popular one, not the only one, but is one of the most used. Now, the JavaScript built the transaction, but remember, we need to sign with a private key. And where is the private key? Obviously, in our crypto wallet. As I told you, MetaMask, for example, is a crypto wallet we can install like applying in our browser. Once we have built and signed our transaction, we send, for example, through HTTP. Now, if our transaction is a query, for example, how much Ether I have in my balance, if it's a query, a read-only question, it is read from the local smart blockchain, and it returns the answer to the browser. But if your transaction implies a modification, for example, send 3 Ether to this smart contract, so now you create a new block in your local Ethereum node for your local blockchain. And then through Ethereum protocol, you're going to share this block to other nodes, and if they verify it's a compliant block, they will join the block to their local copy of blockchain. That's the magic that's the magic behind DApps. Very interesting. Okay, now moment of the truth. Are DApps secure? Well, as far as we know, they are immutable. No one can modify the smart contract because they are inside the blockchain. They are secure because all of us sign the transaction, and anyone can verify the code of the smart contract. So, can go wrong? Well, we have a steal of 10 million here, 30 million there, 60 million over there. So many steals of many millions of dollars. So, fun time. How to hack DApps. Our first example is about an encrypted private data. Let's see this example. We have a betting DApp. So player 1 bet 1 Ether for a number N1. Nobody except the player 1 and the contract itself knows what is the number. On the other hand, player 2 bets 1 Ether to number N2. Again, nobody except the player 2 and the contract itself know what is the number N2. So if the sum of the numbers is even, the money goes to player 1. Otherwise, goes to player 2. That's a fair game, 50-50% of likelihood for each player. So let's see the code. We have here an extractor that represents a player and the number he plays. Then we have a public function. Why is public? Because there is the way how user, in this case player, interact with the contract. And this is a public function that allows players to play. And then we have a private function. Why private? Because nobody except the contract itself can interact with this function. This function contains the logic of how to win. And finally, we have players' data that are private. Obviously, it's private because nobody knows what is a number that the player is betting. But well, at first, it seems secure. What can go wrong here? Well, let's see. Here I show you an IDE. This is the IDE that allows to simulate some test scenarios. And here I have the contract deployed. This is the function play. It's a public function. So in this part, we have the players. Let's say this is player 1. He has 100 Ether, and player 2, he has 100 Ether. So player 1 is going to, let's say, he wants to play for the number 4. Play, no. A second, please. We're going to restart our test blockchain. Great. Now we have we're going to deploy, at first we're going to deploy the smart contract. It's easier. For example, here we have the smart contract. We are going to deploy it. Here we have the contract again. I'm going to be player 1. I'm going to play for number 4. Oops, it fell. Let's see the transaction. Okay, here we can see that every transaction we do is going to be recorded in a blockchain. So despite the contracts protects the number, if we see the transaction inside the blockchain, here we have that this number that at first makes no sense, at the end is saying that this is the identifier of the function, and this is the argument of the function. And as you can see, this is the number 4 in hexadecimal. So we are going to move to player number 2, and we are going to play 1 Ether for number 7. And as you can see, in the transaction, then the second player has played for number 7. So at the end, player number 2 wins the game. So every transaction, this is a lesson, every transaction is going to be visible in the blockchain. So be careful with what you do in the blockchain. Remediation. Any private data should be either stored off-chain or carefully encrypted. There are some references in the slide for you to see them. The next example, integer overflow. Integer overflow, we can think about this with an odometer in an old car. Let's say the odometer reached the maximum value. Then, if the car goes over another mile, it becomes 0. That's an overflow. In example, we have a user. He pays, for example, 1 Ether, and he obtains 1 token. This token can be anything. Could be, for example, points in a platform, number of miles in a flight company, etc. So This is the code for this smart contract. Here we have a variable called balance of. This represents the token balance for each user, and the balance is represented in this kind of structure. Here we have unsigned integer 256. So the number of ether, the number of token can vary from 0 to 2 power 256 minus 1. What happens if we add another unit to this value? It will become 0 again as the odometer. Okay. Here we have the token price that is 1 ether. We have to know that 1 ether is equal to 10 powers 18 way. Way is the minimum unit. It's like dollar and cent. Here we have ether and way. Okay. We have finally a public function to buy token. Obviously, we need a public function. So where is the how much money do we pay? We have here number of tokens, and here we have the price per token. It makes sense. So how much to pay? Well, we have a multiplication between number of token and price per token. We know price per token is 1 ether, and 1 ether is 10 powers 18 way. Now, what we are looking for is a number of tokens that make this multiplication to overflow. So if we, for example, use this really huge number and multiply with this value, we obtain this new value. How is it possible that this huge number multiplied by 10 power 18 give as a result this value? Easy. We are talking about unsigned integer, and we have overflow. So this amount of money is the same than less than a half ether. So in theory, if we pay less than a half ether, we are going to obtain this huge amount of token. Let's see in action. So let's return. Here we have another contract, and we are going to deploy this smart contract. So let me change for this user. I'm going to deploy it. Okay. Let's see. Here we need ether. Okay, I'm going to deploy it again. Okay. Now, here we have the smart contract deployed. We have buy, sell, etc. Let's use this new address that has 100 ether. Okay, we're going to see what is the initial balance of this address. At first, we have 0. Okay, now we're going to buy some tokens. Let's see if we, for example, buy this amount of token. Where is it? We are going to buy this amount of token. We just need to pay this amount of way that it's very low. So here we're going to send this amount of way. And let's see if it works. Okay, the transaction is okay. And let's query again the balance of the user. At first we have 0, and now we have this huge amount of token. And we only spend less, let's see the amount, less than a half of ether. Awesome. Believe me, I'm not a romantic guy, but this is a love poem for hacking. Okay, let's return. Great. Remediation. We have to use math libraries to handle integer overflow. From Solidity 0.8 onwards, they manage integer overflow in a native way. But before that version, you need to use a math library. Final thoughts. The smart contract and dApps in general are in adoption phase. So you have to use with care, because if not, it can lead to huge and sometimes millionary breaches. So you have to use secure design patterns when you develop the smart contract. They have to be born from since the creation in a secure way. It's important a continuous security training for all the team involved in the creation, development, maintenance, and deployment of a smart contract. And finally, you can use some automated scans, but they have a limited scope. So it's important to complement those scanning with manual security testing carried out by especially staff who knows how to read the code, how to understand the logic, and obviously how to personalize and customize the test. That's it. Thank you very much for your assistance.